Hello everyone, welcome to this mini lecture. Um, I wish I could be with you guys all in person. I really do miss you guys, and I hope that you're doing well. But this is how I'm planning on sort of leading the class for a little bit. This may be subject to change. I appreciate your feedback, but at least for this week, this is how I plan to do it. So these mini lectures will kind of be in a format kind of like what you see here. Title, subtitle, and then the relevant reading sections from our textbook that this is sort of based on or it builds from. Then there'll be an outline. The first thing in these mini lectures will be some self-check questions, sort of to see, do you have the prerequisite understanding or knowledge to be able to get the most out of this mini lecture. So that's kind of just to check yourself. I would suggest pausing there and then going on if you can do them. Then there'll be some content, which I've shown here in black. And then there'll be some end of lesson review questions, which are basically saying, did you get out of this lecture what I hope you got out of it? And then finally, I'd like to close most of these at least, maybe all of them, with some kind of practice problem or application that you can kind of do on your own to kind of practice or check yourself. And for most of those, I hope to be able to walk you through them in some way. So here are the self-check questions for this presentation. What does a function look like in C++? How do I call a function in C++ from another routine? How can I pass values into a function? And how can I get a return value from a function? So these are questions that are basically review from previous course content, like the last couple lectures when we were back together. So I expect that you should be able to answer these questions. If you're not sure, take a sec to pause and then move on. The topic for today's mini lecture is writing good functions. This is a collection of wisdom, experience, and advice that I have for you to help you not only write good functions, but good code in general. This is stuff that I was hoping to sprinkle throughout all of the lectures that we had when we were together, but seeing as how we're not together and how it's been a while since we've done functions, I thought that this would be a good way to kind of help us get back on the same page. Writing readable code. The number one thing to do when writing readable code is to use comments often. So you can do that to describe a variable. You can, if you've got a bunch of lines that are kind of tricky or dense or hard to understand, you can use a couple lines and explain kind of in pseudocode what's going on. Maybe you've got a for loop that does some fancy things, or you've got a couple other functions that you're going to call from this a certain spot in your code. It's really helpful a lot of times to kind of take a couple lines and write a couple comments in to explain what's going to happen in the next little bit of code. Sometimes, like maybe at the end of a for loop or at the end of another function, you might want to use a comment to remind yourself, hey, I know that after this block of code, this variable should have, something should be true about this variable. Maybe it has this value, maybe it has, certain conditions associated with it or something. But you might know something about it and you might want to make a comment to remind yourself. You can also use function header comments to describe what's going on more broadly, to describe or summarize a function. So here I have an example function called calchypotenuse, which calculates the hypotenuse of a right triangle based on the other two sides. And it uses the Pythagorean theorem. So here on the top, I have a function header comment in blue, and down below, I have some other comments in green. And so in the function header comment, which I expect you guys to do for your functions, I've got a summary of the function on the top. I describe each of the inputs, I describe the output, and then I say what my name is and I say the date. And you can see the style guidelines for roughly how to do those. There's not a set format. This is one format that I chose here. You can do things a little differently too. But then I also have a number of comments here describing the different lines of code. Now, you don't have to have a comment for every line of code. That would actually probably make your code less readable. But maybe one comment line for every 5 to 10 lines of code maybe more if it's a really tricky section of your code, maybe less if it's a really straightforward section of code. But that's a good rule of thumb, a line of one comment for every 5 to 10 lines of code. All right. All right, so here are some other ways that you can make your code more readable. The first is to indent blocks of code. Now on the previous example, there was a block of code that was part of my function. All of the lines of code and all of the comments that were inside of that function got indented. And the reason I do that is because it shows the reader, you guys and me and anyone else, that all of those lines of code are part of that function. It helps distinguish those lines of code from all the code before it and after it. So it helps organize the code and helps other people read your code. The C++ compiler doesn't care whether your code is indented or not. It'll ignore all of the indentations. But the computer is good at reading things that aren't easily readable. We're not. So it helps us. It's also important to follow consistent style. If you indent using 3 spaces for one part of your code and then indent using like 5 spaces for part of your code, that can be a little inconsistent and can cause confusion, and that's something you want to avoid. You also want to use self-documenting code. Now this is something that's a little bit more vague and less well-defined, but basically it means you want to write your code having functions and variables that are named things that are readable and clear. Now if you do that, then whoever is reading your code just has to read the code to understand what's going on. For instance, in the previous slide, if you just kind of read what's going on, it kind of makes sense because the variables have names that are more or less sensible. But you could imagine if I had rewritten that function with variables like z and foo and squirrel, and you'd be thinking, well, why am I squaring squirrel? What is the square root of foo squared plus squirrel squared? And it wouldn't really make sense. But if you choose things that do make sense, it can help the reader understand what's going on without having to write extra comments. There's some examples in this link here. Now, in addition to making your code more readable, there are some other things you can do to your code before you even write it sometimes that will help make your code even better. So one way that you can design your code better is to write robust code. Now what is robust code? Robust code is code that performs well not only in situations intended by the programmer, you or I, but also in situations that were not intended by the programmer. So for example, if I'm writing a square root function, I might want to check whether or not the value that the user sends to this function is negative or not. If it's a positive number or 0, that's fine, I can take the square root of that. But if they give me a negative value, I might want to handle things a little differently. Maybe give an error, maybe take the absolute value of that number and then return it, maybe. But I'll want to think about how I want to write my square root function. Robust code is also not unnecessarily complex. It tries to be as simple as possible, and that helps make it more readable, and it also helps make it easier to maintain and understand. Typically, robust code checks all inputs and assumptions in a function. So like that square root example, it's a robust code will basically say, for a function, robust function will say, what are all the inputs that I could possibly get? And how should I handle each combination of all these inputs? Sometimes it's easy, sometimes it's hard. But it asks questions like, do parameters have the right values? Are they positive or negative? Are they whole numbers when they should have not been whole numbers? And for each one of these cases, you want to warn the user or generate an error if there's some kind of problem, or resort to a default, depending on what the function should do. Ultimately, what you're trying to do is you're trying to avoid errors that would kill your program. Maybe if I tried to take the square root of a negative number, it crashes the program, quits the program, and there's no error message. I want to be able to be the one to give the user an error message rather than have the computer kill my program. So one of the benefits of robust code is that it's harder to accidentally break it. Robust code works right every time because it always gives you the right errors, it handles every single case, and you're never surprised when there's some value that maybe you weren't expecting. It's okay if there's a value that the user that the user types in that you weren't expecting, because your code is robust and it handles it. Robust code is also easier to change. If you have a function that's very robust and then you change something else in your code somewhere else, it's not going to really affect the behavior of this function because the function is standalone. It works it works well. It does what it's supposed to do, and it's not surprised by anything. Because of this, you'll also have fewer bugs. If you catch errors early when you're developing your code, you don't get surprised by errors later, and they're easier to trace because you've caught them quickly. Another way to make your code designed better is to write reusable code. And what we mean by that is summarized in this paradigm: write once, use anywhere. The idea is if you have different places in your code that do similar things, maybe it's better to write a function to do that thing, and then you can call that function from these two different places, or maybe three or four, or many different places in your program, and it saves you time because you don't have to write that same little bit of code in all these different places in your program. You can only write it in one place and then call that function many times throughout your program. This helps you avoid redundant code. Redundant code means code that you've duplicated, or there's multiple instances of that code throughout your program. A big thing in computer science is to not repeat yourself. If you repeat yourself, there's a chance that maybe if you repeat yourself in one place in your code and then repeat yourself in another place in the code, if you write the same thing in different places of your program, maybe there's a bug because if you have to update one version of that, maybe near the start of your program, you might forget to update that near the end of your program when you do this again. So it's helpful if you just have a single function for it. If you have to change something, you change it once in that function, and then every time that you call that function, that change has happened. So again, with this write once, use anywhere paradigm, it makes your code more readable too. You don't have to have the same couple lines of code, say, many times throughout your program. You can just call another function that you've written, and if you've named it well, then it will do that. So it makes you have less lines of code overall. You also don't have to worry about the details of how a function does something, just that it does it. So for instance, when I call the cosine function through the CMath library, remember pound includes CMath, I don't have to know how the computer calculates the cosine. Somebody wrote a really good, robust bit of code that will take whatever input I give it and will calculate the cosine of it, and it will give me the result. And now that bit of code has been used all over the world in all kinds of C++ programs. So again, reusable functions makes your code more readable because you can just, you don't have to think about how a function is calculating something or doing something. You just worry about, okay, I call this function and it does it. Also, writing code that others can use, reusable code, makes you more valuable to your company or institution. So for example, if you've written code that not only you can use for your program, but maybe your coworker can use, that's really valuable because you've just saved your coworker a lot of time developing and debugging the code that you did. So this can be really good, and there's a lot of people actually that will include on their resumes or CVs some code that they've made and released to the public, online, maybe in GitHub or some other repository. And that's seen as being very valuable. Another way to design your code better is to make it modular. Now, taking some code and making it modular, or planning out how you're going to make your code modular, is probably the most time-consuming of all of the tips that I'm giving during this mini lecture. But it's also the one that can sometimes pay off the most. So in modular programming, every function that you write does one very specific and unique thing, but it does that thing very, very well. And the advantage of doing it like this, so basically what you're doing is you're breaking down a big problem into many smaller problems. And the advantage, of course, is that it's easier to program these tiny, smaller problems, these smaller functions, and it's easier to test them rather than testing one big function. When you do that, excuse me, it's easier to change those functions, the smaller functions. Maybe you got something wrong in one of them. You don't have to change all of the stuff in the big function. You can just change your small function that does this very specific specialized task. You can also understand what's going on in these smaller functions usually a lot easier than understanding a big function. So if I look at, say, 5 lines of code, it's usually easy for me to understand what's going on there. But if I look at like 50 lines of code, it's usually not very easy for me to see what's going on there. So it helps to kind of break up the problem, a big problem, into smaller problems. It's important that when you're doing modular programming that your functions are different. They're filling independent different roles. And I'll talk about an example of this in a little bit. It's also a good thing to do to avoid global variables whenever possible when doing this. You can put important variables like constants or something in a class, which we haven't talked about. We'll talk about that towards the end of the semester. But one last thing too, modular code is reusable code. If I write a function, I can use it then for my application, but maybe I have a friend who would want to use that too, or maybe I would want to use that same function in another code. So for example, in my doctoral research, I wrote an interpolation routine to do 1D interpolation, linear interpolation, between two values. And I ended up using it not only for the little bit of code that I planned it for, but I used it throughout my doctoral research for lots of different applications. And because I'd planned it to be modular, it was easier for me to add a 2D linear interpolation module. It was easy for me to add a 3D linear interpolation routine, and a number of other ones as well. So just kind of in summary with some last tips, when you're writing reusable code, you want to try to design as many of your functions as possible to be reusable, modular, and robust. So try to make all of the functions like that if you can. The main method is a special one. The main method is the first routine that the computer is going to run when it runs your program, and it's always going to be specific to your program. No other program is going to be exactly like yours. No other program will have the exact same main method. So it's not something that you really intend to be reusable. It's something that you're writing for this specific task. It's the functions that the main method calls that might be reusable. So for all other functions, try to make them reusable, modular, and robust. Now, input and output functions are also a little bit special. They usually involve things like from the user or maybe from other files and stuff. And a lot of times when a user types in stuff, they might, try typing in gibberish or garbage values. Sometimes they'll be typing in good values. And you may not know right away, a priori, whether they'll be typing in good values or bad values. So for these, because they're outside of your program's control, you want to add a little bit extra robustness to input and output functions. So you want to make sure that if a user types in a value, is that value actually usable by your program? Does it make sense? And again, we'll see an example of this in a little bit too. So let's try this with an example. So in this example, we're going to do linear interpolation. This is something that a lot of people in sciences will do. Basically, you're trying to estimate a value in between two other values. So let's say in the x-axis here, we've got point x1, and we've got another point x2. And we know that this sum function y of x has values y1 at x equals x1 and y2 at x equals x2. Now we want to find out what the value of y, or estimate the value of y at some arbitrary value of x somewhere in between x1 and x2. So to do that, we can use interpolation. We can say that we'll treat this function y of x as a line in between these 2 points, and at some point x in between these, we'll figure out what point or what value y would be at that point x. So using point slope formulas, you can derive that that value of y will be equal to the one that is given here on the upper left. You can pause it, derive it for yourself if you'd like a quick challenge, or just take my word for it. But now let's code this up. If you want a quick challenge, try pausing it and see if you can write a program to do this. Otherwise, let's go ahead and see an example of this. So here's the code I wrote for a program that would do linear interpolation. So in this example program, I've assumed that x1 is equal to 1, x2 is equal to 5. The function y of x at x1 is y1, which I'm saying is 1.0, and the value of y at x equals or x2, x equals 5, is equal to 2.0, and I'm calling this variable y2. So at some point in between x1 and x2, x, I'm saying let's see what the value of y at x equals 1.5 is. And so using that formula from the previous slide, we can calculate that y is equal to all of this. Then the program will output and say the estimated value of y of x at x equals, here x would be 1.5, is, and then it would calculate the value of y. And then it's done. So how could you write better code here? I'd like you to pause this for a sec, take some notes, jot some ideas down, and then I'll resume with some of the ideas I had, and let's see if you got some of the same ideas I do. So please pause and jot some notes. All right, thanks. So what I said, or what I thought of first was, let's make this code more modular and more reusable. So rather than having this function, or rather than doing all the interpolation by hand, why don't I create an interpolate function, and then anytime that I need to interpolate, I could just call that function. Now in this simple program here, where I'm only needing to interpolate once, that's not very necessary. But it's kind of nice to have this routine here, because if I choose to do some other interpolation later on in my program, or if I want to make another program that does interpolation, now I have a routine that I can just, if I'm writing it in the same program, I can just call it like I did below. And if I have another program that I want to do interpolation in, I can just copy and paste this routine in from this code into my other program. And I don't have to write any more code. I can just reuse it. So let's take a closer look at this. Here's the function that I wrote here. How could you make the function more robust? Now remember, when thinking about robust, what does it mean for a function to be robust, and how can you make it more robust? I'd like you to stop here, pause, and think back to what it means to be robust, and then continue on with me afterwards. So how could you make it more robust? I've said up there is the non-robust version, down below is the more robust version. So what did I do? To make the code more robust, this interpolate function, I've added some checks to make sure that all the input and output values they make sense. So for instance, it doesn't make sense to interpolate between two values if my value x is outside of those values. It also doesn't make sense to interpolate between x1 and x2 if x1 is greater than x2. So what I'm assuming here for this function interpolate is that we have x1, which is less than or equal to x, which is less than or equal to x2. But I'm also assuming that x1 and x2 are not equal to each other. So in this first if statement here in this function, I've got if x1 is greater than or equal to x2, in other words, if my left side point is greater than my right side point, then give an error message and exit. Now, you may recall that usually we use cout for output statements. Cerr basically will do a similar thing. It's just like coutput, but it's usually what you would use if you're going to be writing an error message as opposed to just regular output. An exit will make the program exit. So if I gave bad values for x1 and x2, then I would get this error message and I would exit. But if that's not the case, else, then I have another check. If x is less than x1 or x is greater than x2, what this is checking for is it's saying, is x not between x1 and x2? I should only do linear interpolation if x is between those two endpoints. If it's outside of those endpoints, then maybe I shouldn't be interpolating. So I'm making my code more robust by checking these assumptions. Now, if x is not less than x1 and not greater than x2, then I'll go to the else statement and I'll return the same thing as what I had before. So again, in making the code robust, what we've done is we've checked all the input values and warned the user early if something was wrong. Now, I just wanted to give you guys some extra additional resources. I'd encourage you to choose maybe one or two of these and kind of skim it. I don't encourage you to read all of them necessarily, because I want to make this more with your time, but choose at least one to read well and maybe another one to just kind of glance at. If you see stuff that you're not quite familiar with, don't worry about it. Try to look at and see it, get what you can out of it. So some end of lesson review questions here. I'll just leave this on up here and give you a practice problem as well. Thanks. And that's it. Thank you guys for your time. Have a good rest of your day.